Hello and welcome. In this video, we want to take a look at the Jacobian and how it pertains to changing the variables x, y to polar coordinates or x, y, z into cylindrical or spherical coordinates. You may recall we've done this already, and when we changed the dv, there was this little extra factor of r that came in polar and cylindrical coordinates. And there was this rho squared sine phi that we threw in spherical coordinates. And in fact, this is exactly what the Jacobian tells us we should do. So here's the calculations. In polar coordinates, right, the conversion is that x is r cos theta and y is r sine theta. Theta is measuring the angle from the positive x-axis up to the point of interest. R is the distance from the origin to that same point, right? So there's just a little trick involved here. X equals r cosine, y equals r sine. So the Jacobian of the change, that is the area element, one little square in the r theta plane is going to be converted to something over in the xy plane, and we want to find what the area of that is, and the Jacobian is what does that for us. So the Jacobian is telling us that we need partial of x with respect to r, partial of y with respect to r, partial of x with respect to theta, and the partial of y with respect to theta. So looking at these formulas up here, I can see the partial of x with respect to r is just cos theta. Likewise, the partial of y with respect to r is just sine theta. And then the partials with respect to theta down here, partial of x with respect to theta would be minus r sine theta, and partial of y with respect to theta would be r cos theta. Right, just taking partial derivatives there. Now, do the determinant, and I've got an r cos squared theta minus a negative r sine squared theta, so that minus a negative becomes a plus, and I've got r cos squared theta plus r sine squared theta. Factor an r out, the cos squared theta plus sine squared theta inside the parentheses there is wonderful because there's a trig identity that tells me that's equal to 1, and sure enough, the Jacobian is just r. So the dx dy, which is dA, is going to turn into r dr d theta in polar coordinates, which is what we saw geometrically. Now let's do a similar thing in cylindrical coordinates. In fact, cylindrical coordinates really are just polar coordinates with the z being left alone, right? X equals r cos theta, y equals r sine theta, z equals z. And the Jacobian is now a 3 by 3 matrix, determinant of that matrix. All these partial derivatives, x, y, and z with respect to r, with respect to theta, and with respect to z. And of course, the partials look just like they did a moment ago for x and y versus r and theta. And then x is not a function of z, so that partial is 0. Z is not a function of r, z is not a function of theta, x is not a function of z, y is not a function of z, and the function of z with respect to z is just z, and the partial there is 1. Okay, so it looks like this. And sure enough, expanding down, say expand across this bottom row, 0 times something minus 0 times something plus 1 times the subdeterminant right up here, and we get the r that we had before times 1. Okay, so dx dy dz, when converted to cylindrical coordinates, becomes r dr d theta dz. And there you have what we saw geometrically before. And lastly, we'll look at spherical coordinates here. Spherical, the usual conversion formulas are the x equals rho sine phi cos theta, y equals rho sine phi sine theta, and z equals rho cos phi, where again, rho is the distance from the origin out to the point xyz. The phi is measured from the positive z-axis down, directly down to wherever that point xyz is. And then if you drop a perpendicular down to the xy plane, then theta is measuring from the positive x-axis out to that point, whatever counterclockwise rotation, whatever that angle is theta. Okay. Now, setting up the Jacobian on any one of these things, what order do you put your variables in? with r and theta, we typically do r comma theta, but it could be theta comma r. There's really no reason why one comes before the other. And here, do you think of rho first and phi second and theta third, or is it rho phi theta or rho theta phi or phi rho theta? I mean, there's 6 different possible ways that you could order those things, which means, what, X, Y, Z we typically do in alphabetical order, but again, those could be any way you want. My point being is the setup of the Jacobian here is very highly dependent on what order you list your variables in. And it's going to make a difference whether you get a plus or a minus sign out in front of this determinant. And when we're talking about the area, or in this case the volume, one little cube in the rho theta phi space will be mapped into some little something shape in the XYZ space, and we're trying to figure out what's the volume of that little thing that it becomes. And so it might give us a positive, it might give us a negative. So typically, you just throw an absolute value sign over whatever you get. I'm going to kind of get negative here, and I want it to be positive. Although, I will admit that it's unclear in my own mind how you really keep track of whether you want a positive or a minus. So when I do these Jacobian transformations, when I change the variables from two variables to 2 variables or 3 to 3, I have to have some sort of sense ahead of time whether I'm expecting my integral to come out to be a positive or negative, because I don't have a good notion of how the transformation maintains the proper orientation, because it's so dependent on what order I put my variables in. Okay, so there's a little grain of salt here in that you just ignore the plus or minus sign that you get until afterwards, and then you got to figure out once you've done the integral, should this have been positive or should this have been negative? All right, so when I take the Jacobian here, I actually take this determinant, I get this big thing, and I'm going to slide this over a little bit so you can actually see the whole thing. And I'm expanding down the first column, third column, so plus minus plus. So this cos phi times the subdeterminant that's down in the lower left corner here, minus 0 times whatever, that's going to be 0, plus this thing, which is negative rho sine phi times the subdeterminant that's in the upper left corner there. So all this stuff. Okay. So what I see here is, I see in this first one, there's a rho squared, actually I'm going to factor out a minus rho squared sine phi cos phi from both of these terms, with a cos already out in front. That ends up being a cos squared. Okay. What's left is a sine, thanks to some quick editing, what's left with is a sine squared theta from here and a cosine squared theta from there, leaving this. In the second term, the second thing here, we got to move over a little more to see the end of that. You still can't see the end of that. Anyway, there is a rho sine squared phi, which is in both of those, and I'm factoring that out to do the rho sine phi that's already out there, so I've got a rho squared sine cubed phi. What's left is a cosine squared theta from this first part, and this is a sine squared theta, which is just off the edge of the page there. Here, beautifully, that both of these things in parentheses, this one right there and that one right here, both are just 1. So I've got minus rho squared sine phi cos squared theta minus rho squared sine cubed phi, and I can factor out a rho squared sine phi from both terms, leaving a cos squared theta and 2 of the sine, not theta, cos squared phi, and 1 of the sine phi's is getting factored out, so 2 of them are left for sine squared phi, and then look at that. Sine squared phi plus cos squared phi is 1, and I just get minus rho squared sine phi. And that pesky minus sign, just because I chose the order, rho, I'll move over here. I chose the order rho theta phi. If I had done it rho phi theta, then my Jacobian would have come out positive. Okay, so I'm just going to throw an absolute value around that and say that the dv, which in rectangular coordinates is dx dy dc is equal to dv in spherical coordinates of rho squared sine phi d rho d theta d phi. So those area elements or volume elements that we introduced for these three change of variables were precisely the Jacobian of the transformation from one coordinate system to the other.